We have now a new section which is on sustainability. And the first talk will be given by Professor Armando Pombeiro. He is a full professor jubilado at the Instituto Superior Técnico from University of Lisbon, distinct director of the RDUN University of Moscow, full member of the Academy of Science of Lisbon, and of course a fellow of EurASc.
And also thank you very much for the very nice invitation. I feel very honored to have this opportunity to collaborate with the activities of these two distinguished academies. So, and talk about the possible shift of alkanes from fuels to feedstocks in organic synthesis. So, well, it's not working. Sorry. Okay, now it's okay. Right. So alkanes, as you know, they are major components of oil and natural gas. And they are saturated molecules. Yeah. And they can be linear, cyclic, and that unit that you see on the right, that CH group can be repeated along the chain. And, but in order to use that energy, they have to be burned. So in fact, and when they are burned, as you know, we are losing carbon from the Earth. So that carbon goes to the atmosphere with environmental problems, as all of us know. And to see just the share of this for the, you can see here from the United States in 2021, for energy consumption, about 70%. 70% comes from petroleum and natural gas. And our approach here would be to try to shift that application as non-renewable fossil fuels of alkanes for feedstocks for the since available organic compounds. So if we do this, you see then, in order to satisfy the overall energy demand, renewable energy and eventually nuclear energy as well, their share should increase, should be promoted as primary energy sources. So this reminds me of the Chatelet principle. That is, you shift the equilibrium of the energy towards the since available products, and then renewable energy should be promoted. Yeah. The loss is incredible. And you see, we are losing alkanes, burning them to use the energy. But much worse than that is when we burn them just to destroy, even without using the energy. And this happens when we flare for methane in a number of places. For instance, the Bakken oil shale field in the United States, and it is a NASA picture taken at night. And you can see the illumination at night. It covers a huge area that is comparable to that of Wales. And the energy that is lost just by burning without using any profit of that energy should be sufficient to power Chicago and Washington. And this is not only here. Yeah. You have in Mexico, Gulf, and many other places in the world. So we are losing the alkanes completely, and even without using any energy of that. I think that this is really terrible. So our attempt really is to convince the industry, let us say, in the long term, that alkanes can be used for other purposes, not only for energy. Okay? But for that, alkanes are very inert. So we have to functionalize them. That is, imagine that's unfortunately. Oh yeah, okay, it's better now. So imagine the carbon chain of an alkane, and one carbon-hydrogen bond is cleaved, and then the hydrogen atom is replaced by a functional group with oxygen, carbon, nitrogen, boron, whatever it is. And so this is like, this is just an analogy. If you have a tree branch in winter, it is here, and then in spring it appears with beautiful blossoms. So this is what really we want to do with alkanes, okay? And for that, since they are very inert, we need a catalyst. We need a catalyst to get a functionalized product, an alcohol, a ketone, whatever it is. And we would like to achieve this under more sustainable conditions than those that are currently used in industry. Of course, this is well aligned with the United Nations Sustainable Development Goals, namely the number 12 for responsible consumption and production, but also number 7, for instance, because we are trying to promote the renewable energy share as well as primary energy source. We can trace back 1876, very long time ago, probably the first system that is capable of catalyzing an alkane oxidation reaction. Yeah. And this was an observation made by Henry Fenton when he found that the oxidizing power of hydrogen peroxide was enhanced in the presence of iron, an iron salt. So later we know that this is what is happening. So this is iron 2 reduces the OO bond of hydrogen peroxide, cleaves that bond, and forms hydroxyl radicals that are even stronger oxidants. So this observation of Fenton then was later used for degradation of hazardous halogen organic compounds, for instance, and also later on as an oxidant for an oxidizing systems for alkanes. But really the field started to be developed by this seminal work by Shilov, very elegant work, almost 100 years later, as you can see, where he observed that if we have an alkane, for instance, methane, and that methane in contact with a solution, in the presence of a suitable catalyst, a metal catalyst, and with deuterated acid, yeah, so what happens with time is that some of the hydrogen atoms of the alkane are being replaced by deuterium. So this is very interesting. And he explained in this way, in this equilibrium, where the carbon-hydrogen bond of the alkane, due to the interaction with metal, is cleaved, and then a proton comes out, and the alkyl group of the alkane coordinates to the metal. And so in this way, we transform an alkane into a reactive alkyl species, which is stabilized by the metal, but even so is much more reactive. Then it can undergo further reactions, and eventually methane can be converted into methanol in a low yield. But anyhow, the principle worked. This is a book published by Shilov and also by George Shulpin. George Shulpin collaborated with this, and he visited this very regular every year. Unfortunately, passed away this year. And recently, we edited a book, Alkane Functionalization, yeah, and you can see here, you can see here those almond tree branches that I mentioned to you. This was a picture taken in the Algarve, in south of Portugal, and I advise you to visit if you have time, and, just before Easter. So this is to show you a variety of products that we can get from an alkane by activating this CH bond. So I'm trying along this to avoid formula and to avoid reactions and so on, because most of you are not chemists. But anyhow, just look at the names: esters, amides, imides, organoboranes, carboxylic acid, and so on. So we can do this by activating that CH bond, and so by cleaving it. And this can be done by interaction of the CH bond of the alkane with a metal through the proper orbitals involved in those bonds. And as a result of that interaction, the bond can cleave, yeah, and can get an alkyl. I gave you an example already. Or by reaction with a strong hydrogen atom obstructor, like an hydroxyl radical, I also gave you an example, the alkane is transformed into an alkyl. So there is a homolysis of the carbon-hydrogen bond, and we get a reactive alkyl. So this summarizes the approaches that we have been using for this. That is, we are trying, in fact, to find simple one-pot processes, and so in a single experiment, yeah, under environmental acceptable conditions, to transform an alkane into an organic product with an added value. For that, of course, if we want to promote sustainability, we have to use non-toxic reagents, for instance, different methods to activate the system, not only the classical heating, but also microwave radiation, mechanochemical as well. Sometimes we use ionic liquid or solvent-free processes, and other approaches I'll show you a bit later. And concerning the metal catalysts, we prefer to concentrate on those transition metals here of the first row because they are abundant, they are cheap, and without strong environmental effect. Okay, but in some cases, we also manage to prepare catalysts with other elements, other metals that are not transition metals. They are in main groups, and this, as I show you a bit later, is also an interesting thing. So we try to use elements along the periodic table that are still not in risk of scarcity. As you can see in this European of Chemical Society periodic table, there are various zones, various areas. The green area is the safe one at the moment, and in our ligands, the ligands that are coordinate to the metal in our catalysts, those ligands we use green elements. So there is still plenty of supply. But concerning the metals, although we prefer green ones, but in many cases we are in the yellow region and orange, where there is some rising threat like cobalt, and even in red, like zinc, for instance, gallium and indium, which should be in serious threat in 100 years. And so far it's fine, but in the future, of course, it's better if we replace them by metals that are in the green area. This summarizes the two main types of reactions that we have been doing in our group. So the A is an oxidation. So oxidation, the CH bond is replaced by a carbon-oxygen bond to give an alcohol or a ketone. And further oxidation, we can even get a carboxylic acid. The other one is through carbonylation or carboxylation, reaction with carbon monoxide, and in the presence of suitable oxidant, we can also get a carboxylic acid, but with an extra carbon atom. And a model substrate is cyclohexane. And the cyclohexane, because it is used in the industry, is a very rare example where an alkane is used in the industry. And it can be oxidized to the corresponding alcohol and ketone, and this mixture is called Ka oil, ketone alcohol oil. But you see, high temperatures, 150 degrees, the yield is very low, only 4%, in order to get considerable selectivity of the system. And then this Ka oil in industry can undergo further oxidation with nitric acid to get adipic acid with the ring opening. And adipic acid is fundamental for the production of nylon 6,6. So, but this produces a lot of, since you are using nitric acid as oxidant, produce a lot of nitrous oxide with environmental problems as well. So we need, in fact, to try to find more sustainable conditions for this. And well, we jump along the periodic table with different types of catalysts. Yeah, multinuclear catalysts, for instance, this tetracopper compound. Yeah, multinuclear tend to be more effective. This is quite effective. Also, these can be heterometallic catalysts with cobalt and iron, 4 cobalts and 2 irons in a single molecule. And we try to use water, of course, and use of water as solvent is challenging. It's challenging because the alkane is not soluble in water, and because the catalysts usually are also not soluble, but we have designed them in order to make them soluble. And so we use aqueous acetonitrile as solvent, and they operate at room temperature, and they are more effective than particulate methane monooxygenase. That is an enzyme, a multi-copper enzyme, that can also catalyze the oxidation of alkanes to the corresponding alcohols, of light alkanes. We can go a bit further. So at a later oxidation, that is, we can oxidize also the Ka oil to the adipic acid that I mentioned to you. But now we need a stronger oxidant, and the oxidant is ozone, O3. And a suitable catalyst, in this case, is an iron scorpion. Well, we call it scorpion. It's a name given by Trofimenko because the ligand that's coordinated to iron looks like a scorpion. A scorpion, yeah, with biting its prey. Yeah. And in this way, we can get the double functionalization, you see, we have two blossoms here from the cyclohexane. Now we have two carboxylic acids there. And in a solvent-free system, radiation-free, heating-free, it occurs at room temperature and without evolution of nitrous oxide. So it is a system that we are developing. We can also go further the Ka oil, for instance, in this case, where we oxidize in a tandem process, and so in sequence, we oxidize the ketone to caprolactone. Caprolactone. That is also important because caprolactone is biodegradable polymer, for instance, and we also use a stronger oxidant here, is this peroxybenzoic acid. For catalysts, we use MOFs. So it was already discussed here what's a MOF, and so thank you. I'm not going to tell what it is, but basically, is you see this MOF was prepared by Professor Ilyashenko from Moscow, and we studied the catalysis of this system. And you can see it is a cluster. The greens are in copper, and so it has 5 coppers and 4 cesiums. Yeah, here is a beautiful cluster, and this unit repeats along the 2 dimensions and forms this coordination polymer. It's a coordination polymer. It's a polymer, but the unit is a coordination compound. It's a metal with its ligands. Yeah, and it is a good catalyst for that overall reaction of conversion of cyclohexane into caprolactane. But these catalysts that I'm showing you, they are soluble. That's what we call it. They are homogeneous catalysts. They are soluble in your system, and then there is a problem of separation. And this can be somehow avoided by using an ionic liquid as a solvent. Okay, ionic liquid, and it can also replace the organic solvent. And so no acetonitrile now, no volatile organic solvent. Or we can immobilize the catalyst on a carbon support, for instance, in multi-walled carbon nanotubes. Or we can prepare magnetic nanoparticles. It's so a ferrite in the center, and then it is coated with silica with the catalyst there. And then in the end, we can separate catalyst just by an external magnetic field. So we can also apply ball milling as an energy input, for instance. And then, let us say, we try to use unconventional conditions for these reactions, but the catalysts themselves can be very, very unconventional. For instance, we succeeded in developing some catalysts that are non-transition metals. For instance, with aluminum, bismuth, and so on. And the catalyst is a complex, is an aqua complex of one of these metals. This was initially very surprising, because if the metal is non-transition, the oxidation state is always the same. It cannot be involved in accepting or transferring electrons, but we are in an oxidation reaction of an alkane. So the trick is that the ligand, water is replaced in part by hydrogen peroxide, and is the deprotonated hydrogen peroxide ligand that reduces the OO bond and cleaves it of the hydrogen peroxide to the hydroxy radical. So it is also interesting because theoretical studies occurred before the experimental ones. This was predicted, so Maxim Kuznetsov predicted this theoretical, then we went to the laboratory, and in fact it worked for a number of systems. So here also we found that water can be used not only as solvent. Initially our aim was to have water as solvent, but it can be used as a Levine ligand to be replaced and generate an unsaturated center. Can also be as a catalyst for proton transfers. I'm not discussing the mechanisms, but there's very important proton transfer reactions along the mechanism. And we found also that water can be used as a functionalizing reagent of the alkane. And this is in this reaction that we called it hydrocarboxylation, where you react an alkane with carbon monoxide and water, and the present oxidizing agent to give a carboxylic acid. And the source of this OH group is water, and we proved that by using O18 labeled water in this system. So as single pot, we produce a carboxylic acid using a mixture of water, acetonitrile as solvent. Yeah, and it's very simple, and I will show you much simpler than what is used in industry. And we can also replace the organic solvent, acetonitrile, by an ionic liquid. But water should be always there, because water is a reagent for this reaction. So that system is a development of another one that we studied earlier, and that was pioneered by Professor Fujiwara in Japan, and it's carboxylation of an alkane to give a carboxylic acid with an extra carbon, and using trifluoroacetic acid as a solvent. Of course, trifluoroacetic acid is a very strong acid and is not very convincing. And we found other types of catalysts. Initially, we developed palladium and copper, but we found that some vanadium catalysts could be extremely powerful. For instance, amvadin. This is amvadin. It's a vanadium compound that is present in some amanita toadstools. And this catalyst and models can be very, very effective for this reaction. In fact, they are most effective, as far as I know, for carboxylation reactions of alkanes. So amanitas can be very elegant, and here you have a French version. Yeah, on the left they are poisons and hallucinogenic. The right ones are edible, but I don't suggest you to try that. Yeah, and we like vanadium a lot, so we edited also a book on vanadium catalysis. And you can see here the vanadis goddess, well, paving a way with the amanitas there. Amanita muscaria is also there. Yeah. What I want to stress now is just the simplicity of this process. In one pot, you convert, for instance, methane into acetic acid, and now this is what happens in industry currently. You have 3 different steps, different reactions. First, if you want to start with methane as well, steam reforming, then from synthesis gas, methanol, and then methanol carbonylation to give acetic acid. So drastic conditions, yeah, and so I mean, really, they are not sustainable. So, but our system needs still more green oxidant. We are, for that carboxylation reactions, we are still using peroxide disulfate. But ozone also works for in one of the cases. And so we should try to find, in fact, to extend use of ozone and hopefully of other green oxidants. In order to get an insight into the relevance in terms of publications and also citations of the various types of alkane functionalization reactions, we did a search at Web of Science at the end of last month. And this is the most important reaction of the alkanes. I mean, that one that has been more studied is oxidation. And if you look at the corresponding fields, you see that physical chemistry, chemical engineering, multidisciplinary chemistry, or so, they are more studied, much more than energy fuels. And in fact, this is encouraging because the interest of people is not in using alkanes, it's being replaced from fuels, but for other purposes. So I think this is interesting. This is now the number of publications on the left and number of citations on the right along the 25 years. The other was also along the 25 years. You can see that there is a tendency to increase. So we did this for all types of major reactions of alkanes. I'm not going to bother you with all these plots. Just to summarize, so I hope that I've shown you some evidence that towards the possible shift in the future of alkanes from fuels to feedstocks for inorganic synthesis. So the chemical proof is the one that I've discussed and I have exemplified, and also the Web of Science data. You see the main types of reactions from the literature that where alkanes have been studied. It's an expanding field, but some of these areas are still underexplored, like carbonylation. Others are emerging, like amination or borylation. And it is interesting because the less represented types are those where publications have a higher number of citations per paper. And so this shows people are interested on these new emerging fields, areas. Well, there is also a biological proof that I did not discuss here because they are metalloenzymes that can do it. And there is also some industrial proof, but it's still very, very limited. Still the use of alkanes in this is very, very low. So let us say we can suggest as a useful prospect to try to foster the dialogue between chemical and biological studies and also with the industrial sector. well, this is, let me remind you of next meeting, next year, a bit in the end of this afternoon session. Well, I was allowed to give you a very brief presentation about this, and of course I have to thank all the co-authors. Their pictures were along this, and thank you very much for your kind attention.
Thank you very much for your presentation and aiming to exploit alkanes beyond fuels. So we have time just for a short question, please. So, when you spoke the exploitation towards medical application, you know there are a lot of trends on this area. What could be the great advantage in exploiting alkanes here?
You see, that is one of the emerging areas, really. If you see for instance, the amidation reactions, where you transform an alkane into an amide, and amides can have biological, pharmacological interest. And in fact, that is, if you look at the number of publications corresponding to different areas, scientific areas, and that particular one, the amidation reaction, you see two new sciences appearing. So medicinal chemistry and pharmacology. So really is that's a new field, but we still have, of course, to find catalysts that can operate under milder conditions and with high efficiency and with high selectivity. That's also a problem here. So when you functionalize an alkane, you try, of course, you want that reaction to be selective. But that is difficult because alkanes, you see, you are converting an alkane into a species that in principle is more reactive than the alkane. And so why stop there? Why does not the reaction continue with your product? Because your product is more reactive. And so you for instance, and a general problem we have here is with over-oxidation, where you transform the alkane, for instance, into an alkyl ketone, the oxidation continues and you get CO2. That's the final oxidation product. So that, of course, we don't know. We don't want at all. We want to eliminate all that. So difficulty here is to find a catalyst, a proper catalyst that catalyzes, promotes the reaction, but only the first, until the first or second oxidation state or so, but no further. And so that is not easy to find. And so it's a lot of experiment, really. We can design catalysts, and we have been doing that with a long periodic table with different types of ligands, but before we test, we are not sure that it will work.
Okay, so thank you. Thanks again to Professor. So, we go for the second talk of this section. Will be Professor Luca Volpe. He is the director of the Center of Pulsed Laser of University of Salamanca.
So thanks a lot for inviting me to speak in this very nice place in Madrid. I come from Salamanca, and my name is Luca Volpe, and I was leading the laser plasma chair in the last 8 years at the University of Salamanca, and now I moved here in Madrid, and I am professor at the Politecnica here, very close. Okay, so today my job is a bit complicated because I need to introduce a topic that then will be more or less extrapolated and discussed in several talks. And I just listed Control L. Okay, I just listed, the laser is not working, the pointer, no, okay. I just listed the 4 talks where essentially laser fusion and magnetic confinement fusion will be discussed, let's say fusion. As you know, this series of talks is following a breakthrough that was happening in 2022 in Livermore, and this is a revolution in the field, and this was moving science, politics, and society in the last year, trying to understand what are the next steps that we have to do in trying to optimize and take profit of this very good news. Okay, so I will start by making an introduction about fusion. Okay, so again, the more important point is that we need to identify what are the parameters that we need to work on to try to reproduce fusion. As you know, fusion is 99% of the events that happen in the universe, but still in the Earth, it's a bit complicated, not in terms of science, but in terms of technology. Okay, so let's say that we can summarize the role of this parameter in a criteria that is called Lawson criteria. Essentially, the parameters are the temperature that we need to reach when we confine a plasma, and then the density and the time of confinement. These three parameters are the ones that we need to take into account and control in such a way we can get at the end fusion. So, but what are the reactions that we choose? So this is very clear, and also this will be also explained by Professor Riccardo Betti in the next talk. So I will not go too much on this slide, but just to let's say that there are different possible reactions. We all agree that the deuterium-tritium reaction is the one that we need to use, and we also all agree that doing let's say a work on the equilibration of the energy that we want to get with the laser, we can put together these three parameters, and we can get the so-called Lawson criteria. The Lawson criteria essentially assume that we work with a temperature of around 10 kV, and assuming this temperature, we can say that the product of the density of the plasma and the time of confinement has to be a number like 10 to 14, 10 to 15 particles per cubic centimeter per second. So this is a number that we use then to also to compare the different mechanisms that we can use in the Earth to get fusion. So as you know, the first method you know very well, so it's a gravitational method. So we know that it's working for sure, and it's working also well. And so if we want to try to reproduce this fusion in the Earth, we need to go for other mechanisms. The first is magnetic confinement fusion. Essentially, we can use a very low density plasma, and we try to confine this plasma for a long time. This will be the topic. I don't see here in the audience Tony Donnet. Will be the topic of the presentation of Tony Donnet, that is the scientific manager of Eurofusion project, and he will explain very well what is the status of the project. There is a big project in Europe called ITER that is in Europe, but is an international collaboration. And the idea is that by using a 10 to 14 particle per cubic centimeter times 1 second, you can get the Lawson criteria. But the Lawson criterion can also be obtained by using microexplosions. So the idea of microexplosion is essentially based on the fact that using pulse lasers, you can induce an implosion of a spherical pellet, and by induce this explosion of the external part, you can induce an implosion by following the conservation of momentum, and this implosion will give you the possibility to gain in increasing the density of your fuel by following a volumetric compression. And so this gives you a very strong density that is normally around 1,000 times the solid density. And this method is the one in which that we are going to speak about today. No, this is back. Okay, before going into the details, I think that I was thinking that looking also on the topic of the other talk, I think that my job here is really trying to, even because I come from high power laser facility here in Spain, to try to go through the laser matter interaction and try to explain a bit what are the main mechanisms that are based on this process, and what are the challenges in this mechanism. So what we say when we speak about laser plasma, so laser was having a life alone, plasma also, but when we speak about laser plasma, we speak about a process that produces plasmas that are extremes. What means extremes? So these plasmas are very short in time and are very, let's say, spatial localized in micrometer scale. And to generate this plasma, you use extreme lasers. And when we speak about extreme laser, we speak about lasers that are very short, from nanosecond to femtosecond scale. And this is also, the time scale is also the physics and the technology that divide the type of laser that you can use it. And they are very intense. They are very intense with the intensity of the order of 10 to 20 watt per centimeter square. That is not really the intensity that we use for fusion, but this is the top intensity that we can reach. So what you can do with laser, focusing the laser on matter, you can do essentially two things. So the first on the side is what people do in laser fusion. So the lasers are nanosecond long, and you concentrate the laser in a point that, assuming that we are not in a relativistic regime, so you have a fixed reference, and every time you have a plasma that you can always say that is partially, that is essentially neutral, okay? So it means that every time you do an integral, you see that the total charge are zero, okay, the net charge. And this is mainly related to laser fusion. But then, in 2018, so Nobel Prize to Gerard Mourou and Donna Strickland for the discovery of CPA technique, lasers start to become shorter and higher in intensity. And especially if you are shorter, in sense of the time scale, if you can accelerate particle before hydrodynamics start, it means that you can really do a separation of charge. And so this was introducing the physics of acceleration. Okay, so if you have a short pulse and it also high intense, you can accelerate. So you can generate a particle beam. You can separate electrons by protons, and these give rise to different possibilities to accelerate electrons, protons, and so on. And this is mainly the two things that you can do with lasers. Okay. There are a lot of laser systems, because this is also a very strange way to do physics, because I think that sometimes the companies and the private industry were faster than physics, so they produce the laser and then the physicists say what we do with this is not, for example, like the CERN, that they were building a machine thinking on the Higgs boson. In this case, sometimes you have a laser and maybe still you don't know what to do. So this is particularly strange. So this is just to show you that Europe is for sure a leader in this technology with Asia and America. And here I just listed 3 examples of a laser company. 2 are from France, Amplitude Talents, and 1 is from Germany. And also just to show you that here in Spain we have a petawatt system that is a very unique system that is part of the ICTS map of Spain, that is CLPU, that is 200 kilometers far from here. And you see that the city is also very beautiful, Salamanca. Okay, very fast here, just to show what is the difference in terms of science and in terms of technology about laser. I made an example here, having the same power. And we know that power is the one that essentially, more the power, the intensity is the one that rules the physics. So if you change your intensity, you access to different process. But on the other side, even having the same power, I have shown here an example of a megajoule laser, the energy at the top. And this type of laser provide, the last row here, provide megajoule per nanosecond. So if you do the same, and if you use kilojoule laser, but with a picosecond duration, the same power you provide 6 orders of magnitude less. So you provide joule per nanosecond. And if you go in the femtosecond, you provide microjoule per nanosecond, even at the same power. So this means that the power, it's important to rule the physics, but also the energy give you, in some way, the differentiation of the physics that you can do with different lasers, and also why there are different technology and different lasers. For example, the laser that we have in Livermore for fusion is not the same of the laser that we have in Salamanca, even if the power is the same. Okay, so and then what's happened when laser interact with matter? So unfortunately, the pulse profile of a laser is not Gaussian, because we normally like to put Gaussian profile. So this is just a measurement of the Vega 3 petawatt laser in Salamanca, but they are very similar. Okay, so in this case, the pulse is a femtosecond long, but you see that the temporal profile is very structured. So you have different time scale acting in the same pulse, because you have the so-called amplified spontaneous emission that is long few nanoseconds. Then you have the so-called picosecond ramp, and then you have your pulse. So this means that the laser, if we do an experiment, we focus the laser in a thin target that can be metal foil. I remember the talk before, they say you can buy this foil in the supermarket. Even for us, it's the same. It's 13 microns, the aluminum foil, so it's perfect to do acceleration or something. And then during the interaction, the lasers start to interact with the matter and generate a plasma plume. And this is we call plasma corona. There is a law that gives us a way, let's say, an idea of the opacity or the transparency of the plasma. And this opacity and transparency of the plasma depends essentially by the density of the plasma. So the density of solid is 10 to 23 particles per cubic centimeter. And if you reduce the density by a factor of 2, you go in a density that is 10 to 21, that is normally typical on this value. That is the threshold when the plasma starts to become transparent. So it means that if I have a plasma with a density higher than 10 to 21, the plasma is opaque, otherwise it's transparent. And this is why the laser is not the one that really interacts with the target, but interacts with the pre-plasma that is formed in front of the target. And this means that the laser interacts with which particles? With electrons for sure, and are the electrons that when they are accelerated, they transport the energy into the matter. And this is for what concerns the particle. Then you have the conservation of momentum, because the expansion of the plasma has to be compensated, and then you generate shock wave that travel into the plasma. And so these two mechanisms are the ones that mainly rule in very general way the interaction between laser and matter. So what is inertial confinement fusion? Again, here I will go very short because the talks will be dedicated to this. But the idea is that you shoot on spherical pellet, and the expansion of the ablation, the plasma ablation, is such that you can compress this pellet by a factor of 40. And this is what gives you the density 1,000 times the solid density that is required to get fusion. For sure, this was a very challenging process that will be described later, but now this is just the structure of the target. That again, I don't want to go just into detail, but just to see that normally the target is a solid shell filled by deuterium tritium gas, and so it is made by two different densities. And the idea essentially, you cannot ignite all the pellet, but normally people in Livermore try to compress until they reach the so-called hotspot, and then when the reaction starts in the hotspot, the alpha particle do the job to make the burning phase, so to transport the reaction in all the target. Okay, so what are the problems? Here again, if you try to compress a spherical pellet, it's like to try to compress water with your hands. So you have a lot of hydrodynamic instabilities that essentially depends on the growing up of spatial instability in the separation between the two different material. And these are very well known. We know how to control. Okay, so we know how to control theoretically, but this was one of the main reasons of a strong delay in getting fusion in Livermore, because all the steps that scientists in Livermore did were trying to optimizing the quality of the target, the roughness, the aspect ratio between the shell thickness, just to try to reduce not only this, but hydrodynamic instabilities. But again, I think that Professor Riccardo will go more through this. And then let's go to the second part that is more related. Okay, what we do now. So the method that has been used in Livermore is the so-called indirect drive method. Again, the indirect drive method is only possible to be used in two laboratories. One at the moment, that is NIF in United States, Livermore, and Laser Megajoule in France, in Europe. This is a military installation, so also for this the science is not going very fast, also because this is not the primary goal of the facility. So the direct drive approach is different with respect to the indirect drive, because in indirect drive, what you do, you focus your laser in the internal part of a cavity, and this cavity is coated by aurum, and you generate a bath of soft X-ray, and these soft X-ray are the one that focus on the pellet and produce the plasma ablation. On the direct drive approach, you skip this part and you focus the laser directly, and this is giving to you for sure a factor of 2 in gain in principle. Okay, so the breakthrough that was happening in December will be discussed by Professor Riccardo Betti, so I will go faster. And I will go so fast on the National Ignition Facility that will also be presented, but is a huge installation of laser, and also LMJ is very similar, but still is on delay on this point. Okay, I will go directly to the challenge. So now, what was happening in Livermore is that they get a gain that is defined as the ratio between the energy, the laser energy, the nuclear energy that you get with respect to the laser energy that you input. But if you calculate the electrical energy that was necessary to produce a laser, for sure you have a factor of 100. And this factor of 100 is estimated to be necessary to make a realistic power plant, with also the addition of a necessity to work at 10 Hertz. So 10 shots per second, a gain of 100. The idea of direct drive, again, is to push and focus the laser directly on the pellet. The problem is that this approach is prone to uniformity problems, hydrogen stability, and also we will see parametric instability, so problem of exchange of energy during the interaction. So the solution that the people was thinking is just to separate the phase and do a first part of compression that is not so strong, it is not requiring to generate the hotspot, and then separate in the second phase where you essentially spark your target, trying to get the energy required, and you can spark with different projectiles. You can spark with electrons, you can spark with protons, and this is called fast ignition, or you can spark with a shock wave. Okay? So the first approach was fast ignition by using electrons. Unfortunately, this is not anymore. I mean, someone still is studying, but the problem of the divergence of the electron was very strong and was reducing too much the energy deposited in the center of the pellet. So at the end, this is still, let's say, that is paused, okay? Then you have proton fascination. This is also an interesting scheme. It is based on the fact that you deposit the energy by using protons. The proton can be produced by laser interaction. The problem is that you need to have a target that is out of the pellet. Let's say for thinking in high repetition rate system, this probably technologically is a bit problematic, but it's based on the fact that proton deposit the energy exactly in the center of the pellet due to the Bragg peak property. The shock ignition approach for sure will be also, I don't know if Ricardo will speak about a bit on this. He was proposing the scheme, so I will not go through too much, but it's based on using shock wave. Essentially, you just manipulate the laser pulse, putting a final spike at the end that is the projectile that you use to generate the hotspot. So these are the facility. I will go faster, and I will go on the hyper project. So I have still 2 minutes. Okay, 2 minutes are perfect. So in Europe, there was a project based on a direct drive approach. It was started, so I think that also Professor Manolo Perlado will speak about this. This project was mainly devoted to study direct drive approach in Europe. Unfortunately, due to the delay in United States in reaching fusion, the project was stopped. So there are some other projects that are supporting inertial confinement fusion community in Europe, but are very few. And what we started to do after 2021, there were a lot of changes, not only in terms of academic and laboratory approach, but also in terms of a private company. There were a lot of private companies that grew up, and due to this, we also made an initiative that we call HyperPlus, that is essentially made by 15 scientists and supported by more than 100 scientists in Europe and abroad. And the last goal of this initiative was the roadmap. We publish this document. It is accepted for publication. We are just correcting the proof. And this is the first step that Europe is trying to involve in trying to come back with a coherent, structured European project on laser fusion. The last is just that also in Spain we are doing something. We start to move. We made the first satellite meeting in Gran Canaria in September, and this meeting was with more than 35 scientists from Spain, and representing 15 different institutions, laboratory, university, and so on. And this was essentially made by collecting and try to gather Spanish research activity on laser plasma and inertial confinement fusion. I'm sorry if I was too long, or I'm okay, so I can just say thanks.
Override the time. I don't know if someone wants just a short question, because otherwise we need to move because we are a little bit delayed. Any question? Because we just saw what are the facilities and mainly what Spain aims to do and exploit this laser. So, okay.
Okay, thank you. This was absolutely fascinating, and it reminded me a little bit. In a sense, you're doing a Manhattan project here. There are different teams who are trying to work towards this. And I'm wondering, who's the Oppenheimer in this?
No,
who's the Oppenheimer in this group?
In Europe, the HyperPlus community, it's really, let's say, at the moment, anti-Manhattan, so it's democratic, but will not be, for sure, the last point. What we did, we tried, because in Europe there was and there is a community in ICF, but the last 10 years was a bit dispersed because of lacking of a project. What we're trying to to do in the last 2 years is to make some container of ideas of collection of possibilities waiting for an European project. What we are trying to do now is that we will apply for ESFRI to enter again with a new project in ESFRI roadmap in Europe and try to get some money to prepare a TDR in such a way that we can try. But the Hyperplus is even a bit more. So we are also thinking to try to work for a university, to make a course, to make Erasmus, just to try to put the water in the tree and try to leave things happen, let's say.
So let's thanks to the speaker. Let's we now move to the last talk of this morning, which is Pat Smith from University of Aberdeen, and he will give his talk by Zoom. So we are a little bit.
This.
Good morning, everyone. Sorry I can't be with you today, but I'm very glad to be able to give this presentation by Zoom. I'll just share my screen, which hopefully you could see in full screen now. So I'm going to be talking about some of the work that we've been doing on the environmental sustainability of land-based renewables over the past 20 or so years. I'd like to preface this by saying that this is not, by looking at the sustainability of renewables, this is not in any way excusing or circumventing the need for the phase out of fossil fuels. If we look at this graph here of what we need to do to get to net zero or to retain the temperature within the 2 degrees Celsius or the 1.5 degrees Celsius temperature target that we agreed in the Paris Agreement, the greatest chunk of the abatement or the emissions reductions come from conventional abatement technologies. So this is really to do with replacing fossil fuels with renewables and nuclear. But I'm going to be talking mainly about renewables today. What's also shown on this graph is that even though we do our best to reduce greenhouse gas emissions by conventional abatement technologies, there are still going to be some emissions in the mix going into the future through things like agriculture, which emit greenhouse gases, which are very difficult to abate. In order to balance those positive emissions, we need some negative emissions. That's shown in blue at the bottom, where we use carbon dioxide removal technologies. Now, that's not going to be the focus of the talk today. I'm mainly going to focus on renewables, but I'm just mentioning it because it does come back later when we're talking about bioenergy, particularly when we talk about bioenergy with carbon capture and storage, because this is a prominent carbon dioxide removal technology. So the three renewable technologies that I'm going to speak about today that we've done some work on over the past 20 years are bioenergy. That's using biomass and burning that biomass to replace the energy that we generate from fossil fuels. Wind energy, and we compare those to solar energy later in the presentation. So let's have a look at bioenergy first. Now, why is this important? It's important for reducing emissions. If we look on the left of the graph here, on the left of the slide, we can see that when we burn fossil fuels, we release CO2 into the atmosphere. That's CO2 that has been locked away from the atmosphere for maybe 300 million years. So when we burn it, we release that CO2 into the atmosphere, and that increases the atmospheric CO2 concentration because we're releasing it. It's been locked up for many hundreds of millions of years, and we release it over the space of years to decades, and that increases the CO2 concentration in the atmosphere. If you look over on the right of the slide, bioenergy is using plants that we grow biomass. As the crop grows, it fixes carbon dioxide through photosynthesis. Some of that is released through respiration, but some of it is incorporated into the plant material as the plant grows. And when we burn that, for energy, we release that CO2 back into the atmosphere, but that CO2 is carbon dioxide that has just been captured over the last year or the last few years. So this is roughly carbon neutral. The biological carbon dioxide is being recycled over the time scale of years rather than releasing fossil carbon dioxide into the atmosphere. So there's no net increase in atmospheric CO2. What we can do further, as I mentioned earlier, with BECCS, that is bioenergy with carbon capture and storage, rather than allowing the CO2 to go into the atmosphere, we can capture that CO2 and we can liquefy and pump it underground into geological storage reservoirs, saline aquifers, and depleted oil and gas reservoirs. This is an example from Hokkaido in Japan of one of 10 or so schemes that are set up as experimental schemes, and they're now working to pump CO2 underground into the atmosphere where it's in long-term geological storage. So that's bioenergy and bioenergy carbon capture and storage. And I'll just give you some examples of how we've looked at the sustainability of this over recent years. So we first started by developing models to estimate the bioenergy growth potential and to calculate the greenhouse gas emissions that could be possible from replacing fossil fuels with bioenergy. The models are sort of typical crop growth models. They respond to climate, soils, management for each crop type. This is just a graph showing the potential over Europe. The green areas are showing larger area, larger biomass potential and larger greenhouse gas removal potential. And the redder areas are showing smaller potentials. But we quickly moved on from just looking at the potential to grow biomass and started looking at the impacts of energy crop growth on ecosystem service. It's very important to note that the sustainability depends on what you're replacing. So if you look over here on the right of on the left of the figure, we can see here that this is energy crops, miscanthus, short rotation coppice, and short rotation forestry, replacing arable. So this is where you're placing energy crops on former cropland. In the middle, it shows what happens when you replace energy crops on former grassland. And on the right-hand side of the graph of the slide, it shows what happens when you replace forestry or woodland with energy crops. And what you can see over on the left-hand side, when you replace arable crops, there's largely a significant improvement on ecosystem services, particularly on regulated services, hazard regulation, disease, pests, pollination, soil quality and water quality. On the provisioning services, the only one that there's a negative impact for is in terms of water availability, because energy crops tend to extract more water, use more water than annual crops. When we look at, we've got more of a mixed situation in the centre where we look at replacing grassland, and we have largely negative impacts where we're growing energy crops on former woodland or forestry. So it makes no sense to chop down trees to put energy crops, but if you can find underused cropland or cropland that's no longer used or abandoned, you can provide some benefits to ecosystem services through growing energy crops on this land. We further looked at the potential for bioenergy with carbon capture and storage. This is an example from the UK, where we looked at centralized and distributed versions of bioenergy with carbon capture and storage. The locations where you can do bioenergy with carbon capture and storage is limited by the access to the pipelines for the carbon that you captured that can then place that CO2 underground. So we can look, we've got 59 sites here that are potential sites for bioenergy with carbon capture and storage. And we've assessed the potential to grow energy crops within a radius of these potential sites. And we've also assessed the impact on air quality and water quality and soil quality. So we find that we can get CO2 reductions of approximately 18 to 23 megatons of CO2 equivalents per year in Great Britain. that can be accompanied by reduced agricultural greenhouse gas emissions by between 9 and 11 megatons of CO2 equivalents per year. And we find that there's also positive impacts on reduced soil ammonia emissions. So that's important for air quality, reduce water pollution from soil nitrate leaching, and increases in soil organic carbon. So if this is appropriately sited, bioenergy with carbon capture and storage could have positive impacts on a range of ecosystem services. This rather complicated graph was in a paper that we published in Nature Climate Change in 2016. But what I want you to focus on is the BECCS item in the top left-hand corner of this figure. What it's showing is that there's quite a high potential for removals of emissions. So this is at the global level, and we're looking at the removal of about 3.3 gigatons of carbon per year, possible with bioenergy and carbon capture and storage. And it also produces energy. So the energy cost is negative. So that's why it's over on the left-hand side. So it can also produce energy. But it does have quite a large land footprint. If you look at the color of the dot, it's got a land impact of maybe 400 to 600 million hectares would be required in energy crops per year. And it's got quite a large water footprint as well, with quite a large impact on the use of fresh water. So whilst there can be some positive impacts, there are also impacts on land, water, and it's also got quite a moderately high carbon cost. And lastly, we've looked at the impact of BECCS, bioenergy with carbon capture and storage, on nature's contributions to people and the Sustainable Development Goals. So what's shown in the center of this pizza diagram are the functions that are provided by BECCS. So those are largely in terms of energy that it provides and in terms of carbon sequestration. That's shown in the green ring in the middle of the pizza. In the middle ring of the pizza, the grey ring, it's showing the impact of those functions on nature's contributions to people. So these are the ecosystem services that are provided, that we all rely on, and the impacts, the positive or negative, that bioenergy with carbon capture and storage has on these. The little green circles are showing the positive impacts, and the white circles are showing the negative impacts. So there's a negative impact on habitat creation, regulation of freshwater quality, and on food and feed, largely due to the large areas that are required to produce bioenergy. And we can further look at the impact on the Sustainable Development Goals, the United Nations Sustainable Development Goals, that's shown in the outer ring of the pizza. And this is showing positive and negative impacts of the different nature's contributions to people that I've just described on the Sustainable Development Goals. So when you see a little white circle on in the outer ring, this is showing a negative impact, and a dark grey circle is showing a positive impact. So you can see there's a mix of positive and negative impacts on the Sustainable Development Goals from bioenergy, carbon capture and storage, with potential negative impacts on Sustainable Development Goals 2, 3, 6, 8, 12, and 15. So there's some work to do. It's really important to quantify these potential risks, because it's only when you understand the risks that you can then manage them when moving forward. So now let's have a little look at wind energy. So wind energy is a great option for replacing fossil fuels, but it really depends where it's sited. So we looked at putting wind farms on peatlands. This is something that's being done in Scotland and in the UK, because peatlands are areas that are a long way from anywhere, a long way from people, so they're quite an attractive place to put wind farms. But we've shown placing wind farms on peatlands doesn't give a net benefit in terms of carbon dioxide removed from the atmosphere. That's because the construction of wind farms on peatlands causes large losses of the peatland carbon. Carbon in peatlands is a huge stock. peatlands contain a huge stock of carbon. And when you put roads or turbines on peatlands, you have to drain the peatlands, and this causes large emissions of carbon. So as the energy mix decarbonizes in the UK, so as we gradually move towards renewables, it gets more and more difficult to offset that carbon that you lose by placing the turbines by the energy that you save from fossil fuels, because the proportion of fossil fuels goes down in the mix. So we showed that by 2040, wind farms on peatlands will offer no climate benefits over their 25-year lifetime of the turbine. That's even if there was no drainage at all. And we know that there is drainage required for the roads and for the turbines. So it's important to site wind farms on mineral soils, that's the non-peatlands, and avoid building them on peatlands. And this was a paper that we published in Energy Policy, and we had a little commentary piece in Nature on this, as showing the disbenefits of wind on peatlands. So wind is a great option, but don't build wind farms on peatlands. That makes no sense whatsoever. We've also looked at the biodiversity impacts of wind expansion. So this is looking at the potential areas of wind expansion. And we've mapped these onto areas, onto ranges of birds, different bird types. And we found that the ranges of heavier soaring bird species and bird species that are migratory overlap more with the ranges of the places where we would seek to site wind power. So these areas of conflict between soaring bird conservation and the potential for wind energy development could be large. So these areas of potential conflict are largely unprotected at present. So we have to make sure that we site the turbines in a way that minimises these risks. So understanding the risk, again, is important to put in place the mitigation that allows the adverse effect to be minimised. But it's important to note that wind turbines have a relatively small impact. If we look at bird mortality, this is from a paper we published in 2015. This is data from the US over a range of years. Wind turbines are responsible for about 140,000 bird deaths. That sounds quite a lot until you compare it to the 14 million bird deaths that are due to fossil fuel power plants, and the 365 million birds that are killed on buildings and windows. In fact, domestic and feral cats are responsible for 210 million, and the transmission lines from conventional power plants about 174 million bird deaths. So the fact that wind turbines do cause bird deaths, that's often in the news, but it's not compared to the conventional infrastructure that it replaces, which is actually responsible for far more bird deaths, orders of magnitude more bird deaths than the wind turbines themselves. So I'll just finish by looking, by comparing the renewable energy sources, comparing bioenergy with wind energy and with solar energy. So this is a paper that we published in 2013, which was looking at the energy growth potential, the energy generation potential from energy crops, from solar PV, and from wind turbines, both unconstrained, and then constraining this by the land use, the cost, and the carbon. And what we can find is that there are large areas available. If we have a look over here at panel D, large areas that are available for growing energy crops. That's basically, you can grow them anywhere you're growing any other plant, but the energy generation potential is quite low. Compare that to solar, there are smaller areas available that are much greater energy generation potential, particularly in these very warm and sunny areas, and a great potential for wind turbine, in fact a bit larger than for bioenergy in places, but fewer areas where this has the greatest potential. So this shows that in terms of renewable energy in the future, maybe bioenergy has a more limited contribution compared to solar. As solar costs, solar PV, the costs have fallen, and the levelized cost of energy are now much cheaper than that of fossil fuels. So that looks to be the best option, combined with wind, with maybe bioenergy playing a smaller proportion in the mix than we had first thought. We can also compare the impacts on biodiversity. So this is looking at the overlap between the areas that we can grow energy crops, the areas where we would site wind energy, and the areas where we would site solar. And looking at the overlap with protected areas. So shown in green are the existing protected areas, and shown in blue are the areas that are likely to expand, the protected areas that are likely to expand in the future. And what we find is that bioenergy production is a major potential threat to biodiversity, whilst the impact of wind and solar appears to be smaller than that of bioenergy when we look at future conflicts with bioenergy in the future. So the last slide that I'll go into in detail is taking a full LCA approach, which is important when we compare bioenergy. But the other important thing that I want to get across on this is that we have to look at the counterfactual. So it can come across, I guess, in this presentation that I'm providing loads of details of negative impacts of, for example, renewable energy. But what we have to compare that to is the natural gas, the fossil fuels that these potential renewables replace. And we find that bioenergy and in fact other renewables have far fewer negative overall impacts than the natural gas which it replaces. And that can be shown over here on the left. The red areas, are those where you have significant negative impacts, both local and globally. And if we compare those, you see far more areas in the red and the orange for natural gas compared to bioenergy. So that emphasizes the importance of comparing the renewables with the polluting fossil fuels that they replace, so that we don't get an undue opinion that renewables are going to be causing problems that are not there already with fossil fuels. The fossil fuels are already causing these problems. So in conclusion, we need to wean ourselves off fossil fuels and to generate the energy we need with renewables. That is a given. We understand that very clearly, and nothing in this presentation should be taken as any way I'm backtracking on that. But renewables are not without their side effects. It's important to assess these side effects so that we can manage the risks going forward. The environmental impacts of renewables are almost always lower than the impacts of fossil fuels and the infrastructure that supports them. So it's important to compare. When we're doing a comparison between energy sources, we also compare them to the fossil fuels that they replace. And we must make sure that we compare our renewables to those old polluting technologies going forward. We need renewables, but it's important that we choose the right ones and that we situate them in the right places. Thank you very much for your attention. I hope you enjoy your lunch. Thank you.
So thank you very much for your and you kept it on time. So we have a pre-lunch speaking with you. So any okay.
Thank you, Professor, for a very interesting presentation. Concerning the generation of energy with wind, especially the wind farm on the sea, they produce a negative effect on the air traffic control radar and the air defense. This has been clearly evidenced in the recent International Radar Conference that was held in Edinburgh last year, in November last year. It should be considered.
Yes, that's a very good point.
Yeah, it should be considered, especially in this period of.
Yeah, that's a very good point. So there are other things other than ecosystem services that we need to consider when we're considering which renewables to use and where to site them. I quite agree with that. That's a very good point. Thank you.
So any other question? I have one. You said that we have to select what are the appropriate technology, in fact, and how this will impact on the environment. But how you will make this type of selections when we have all this pushing that we need energy, and how you will solve this problem and keeping comfort to everybody, and if you go to make another layer before taking decision.
Yeah, it's a very good question. I mean, we definitely need to move to renewable energy without greenhouse gas emissions, and we're all aware of that to tackle the climate crisis. But we do have difficult choices to make, and all of these things can be taken into consideration when we choose to move to renewables. A large thing that determines the move is the levelized cost of energy. And those have dropped dramatically for solar PV and particularly for onshore wind, but more recently for offshore wind. So I think these are going to go up in the proportion of the energy mix in Europe in the near future. But understanding these potential risks and potential trade-offs allows us to manage and site those renewables in a better way. So it doesn't mean that there's necessarily an extra layer of decision making that happens, but understanding the threats to ecosystem services that renewables present, it allows us to better manage them in the decision making of policymakers. So the transition is inevitable, but having the information allows us to manage that transition in a way that minimizes the risks.
Okay, thank you. Okay.
Thank you.
Pete, thanks very much, John Porter here. Pete, I mean, if you look at the triple point...
Hi, John.
Hi. If you look at the triple point diagram for CO2, you know, the relationship between pressure and temperature, if you get pressures around about 1,000 atmospheres, then actually you move from CO2 as a gas to CO2 as a solid. And I mean, and do you think, I've been thinking about this, and if you were able to move CO2 down to the very deep parts of the ocean where you have pressures well over 1,000 atmospheres, then you would be turning CO2 from a gas into a solid. And we already have the drilling rigs that, you know, that go down as far as 2,500 meters. I think we also need to think a little bit out of the box here, because I mean, I'm really not optimistic that we're going to stay below 2 degrees, and I think we have to think about how we can get maybe rid of 40 gigatons of CO2 per year out of the atmosphere and into a stable situation down at the bottom of the deep ocean, like the Manila Trench, for example, where the pressures are well over 1,000 atmospheres. And then you would, because CO2 sublimates, it doesn't go through it. You can have liquid CO2, but it basically sublimates back from gas into solid. And if you rate, it's maybe a medium-term solution, but I think we need to be thinking about these medium-term, and you know, because we got 7 years before, and we've got to get rid of our decrease in emissions has got to be 7% per year for the next 7 years. And we're still emitting at 1.3% per year. So we're in a desperate situation, really.
Yeah. We are. Yeah, I quite agree, John. There's adequate space for storage in geological reservoirs. So I think we should exploit those geological reservoirs as far as possible. But it's true that there's the potential to store it in the deep ocean. I know the Monterey Bay Research Lab have been doing some work on pumping CO2 into the seabed. I don't think it's as deep as some of the depths that you're suggesting there. But it certainly has been. It's in the testing phase. People are looking at that, and we do need to find those solutions to where we're going to store that CO2. I think we can max out our geological reservoirs, but we should be looking at the other options to see if they're in terms of their safety, in terms of their the lifetime of storage, and in terms of their environmental impacts. That's a good point, John. Thank you.
Okay, so let's thanks to our speaker and to all the speakers of this morning sections, and go to the lunch. Thank you.